Logarithmic functions are the inverse functions to exponential functions. That's certainly one way to look at them. So let's do that in detail. Let's look at an exponential function and then very closely look at its inverse, and from that we can get an idea of what the logarithmic function is. So let's do something simple. Let's do f of x equals 2 to the x. Okay, and let's fill out the table. Let's do a point table like so. Okay, with some values to get a nice plot of this function. Okay, so we have perhaps, let's do -3, -2, and so on. Then for y values we have, well, let's see, 2 to the power of -3 is 1/8. 2 to the power of -2 is 1/4, and so on. And we can graph this function the same way we've done in the past. So let's graph this exponential function. Okay, so -3 goes to 1/8, something like this. -2 goes to 1/4. Okay, -1 goes to 1/2. 0 goes to 1. 1 goes to 2. 2 goes to 4. And 3 goes to 8. And there's our exponential function. Now let's look at the inverse of this. So I'm going to take the same function and just switch it. So now I'm going to do x and f inverse of x. And we're just going to go backwards with this. So instead of going from x to y over here, we're basically going to go from y back to x. So we're going to start with 1/8. And we get back -3. Put in 1/4, we get -2 back. Put in 1/2, we get -1 back. I'm just going backwards on this original table that we had. So when we put in 1, we got 0 back. Okay, whoops. 1, we got 0 back. When we put in 2, we got 1 back. When we put in 4, we get 2 back. And when we put in 8, we get 3 back. Okay, and these values in the right column here, these are our y values. So we have our x's and our y's. Okay, well, let's plot these and see what happens. So we have 1/8 comma -3. So that's way down here somewhere. Okay. 1/4 -2, right about here. 1/2 -1. 1, 0. All right. 2, 1 up here, 4, 2, there we go, and 8, 3. All right. Connect all these up, and we have our logarithmic function. And we write this as log base 2 of x. We say log base 2 of x. Log base 2 of x. And when we write it, this 2 is down in the subscript. So the log and the x are in the same line, and the 2 is shifted down a little bit. And remember that anytime you graph a function along with its inverse on the same set of axes, they will be mirror reflections across the perfect diagonal line y equal x. And note that that same phenomenon happens here, right? We have our perfect diagonal y equals x, something like that, more or less perfect diagonal. And look at the symmetry, right? These are perfect symmetries across that line. If we folded the graph along that diagonal line, these would line up perfectly. So one of the main reasons we spent all that time studying inverses is so that we could understand how logarithmic functions are related to exponential functions. Now, we could have just as easily started with log base 2 of x as our fundamental function and then computed the inverse and called the inverse 2 to the power of x, right? It's not like 2 to the x is somehow more fundamental than log base 2 of x, right? They're both very commonly used functions, and it's good to think of them both as inverses of each other. Now, let's look more closely at this graph of log, because you want to be able to graph logarithmic functions. There are some points that really matter here. Let's see here. This one, 1, 0 is an important point, and 2, 1. Though other points matter as well, the 2 anchor points you want are those 2, and I'll say more about that in a minute. But let's look at the domain and range of this graph. So we're just looking at log base 2 of x. The domain, okay, so the domain means we're squishing everything down onto the x-axis. Just of this second graph here. Don't even worry about the 2 to the x graph. Well, if we squish this down onto the x-axis and up here, it looks like it touches the y-axis, but it actually doesn't. It just gets infinitely close to it. So the domain is 0 with an open bracket here, a soft parenthesis, up to infinity. There's the domain. Right? It doesn't quite hit 0. It gets infinitely close to it, but doesn't hit it. Right? If we were to just color in the portion of the x-axis that is covered by this thing, and then it just keeps going off forever to the right. How about the range? For the range, we imagine squishing this whole function over onto the y-axis. Well, it's pretty clear what happens down here. It just covers the whole y-axis. And then we just squash over, squash over, squash over. And this function does keep rising, granted very slowly, but it does keep going up forever. So if we kept squishing it over to the left, eventually we'd cover the entire y-axis, both all the way down to negative infinity and all the way up to infinity. So the range of this thing is negative infinity to infinity. And this will hold for any log base b of x. I guess as long as b is greater than 1, which it usually is if you're graphing this. Note that this is exactly opposite of the domain and range of 2 to the x, or actually any b to the x. For b to the x, the domain, and we'll model it here off of our 2 to the x, our domain is negative infinity to infinity, and our range is 0, but we're not touching 0, so I'm going to use the soft bracket to infinity. Okay, so these functions are opposites of each other, which makes sense because they're inverses. So of course their domain and range are going to be swapped. So I guess if you ever forget the domain and range of log base b of x, you could just find the domain and range of b to the x and then switch it, and it would give you the domain and range of log. Now in general, let's talk about graphing any log base b of x. Right? Because you never want to use tables to graph. You want it, even though I just did it, right? You do it once to get your graphs, and then you never look back, right? Plotting points like this is a bad way to graph things. So let's do in general. Okay, in general, here's the general graph of log base b of x, assuming that b is greater than 1. Here we go. Let me just get some axes going here. Looks like this. It goes through 2 crucial points. It hugs along the axis, the y-axis, asymptotically approaches the y-axis but never touches it. And then it always goes through this point here, which is 1, 0. Very, very crucial point. And then it keeps going and going off to the right, and it kind of bends over, right? It gets bowed over, really. And it takes until b, whatever b is, to get up to 1. Okay, so it takes until b to get up to 1. Till b to get up to 1 on the y-axis. And you can use that to graph any logarithmic function. So for instance, maybe you want to do log base, I don't know, 5 of x. Okay, no problem. Your axes always goes to this single point, 1, 0, and then 2, 3, 4, 5. So here's 5, There's 1. It takes until 5 on the x to get up to 1 on the y. There's the 2 points that really matter. Asymptotically approach this y-axis. Don't ever touch it, even though mine kind of looks like it did touch it. And it bends over, goes off like this, and then it just keeps going to the right like that. So if you know these 2 anchor points, 1, 0, and this one here is always, I guess we should label that. This is b, comma 1. Just like down here, this is 5, comma 1. If you know these 2 anchor points, that's enough to get any logarithmic function graphed. And then, you can shift those. The standard shifting, stretching, reflections all apply still. But we can treat this as a new base function to add to the library of functions.